Today we will be discussing the paging technique, which is the third memory allocation technique, and this is a continuation to the memory management part 3. So our objective is to explain various techniques of allocating memory to processes. In the last two tutorials, we have discussed the memory allocation techniques, namely contiguous memory allocation and segmentation. Today we will be discussing the paging scheme, which is coming under non-contiguous memory allocation. So as a quick recap of the previous tutorial, in which we discussed the concept of segmentation. Segmentation is a memory management scheme that supports the programmer view of memory, in which the logical address space is a collection of segments and each of the segment is referred using two tuples, namely segment number and offset. And using a segment table, the two-dimensional segment address is mapped onto one-dimensional physical address. So today we will be discussing paging technique. Paging is a memory management scheme that supports the physical address space of a process to be non-contiguous, similar to that of segmentation. But in paging, there will not be any external fragmentation, and also it avoids the problem of varying sized memory chunks. And this is a technique that is used in almost all operating systems, those ranging from mainframes to smartphones. And paging concept is implemented with the cooperation of operating system and underlying hardware. So what is paging? First we will be seeing what is the basic technique or basic method of paging. In paging concept, we are having two terminologies, namely frames and pages. That is, the logical memory will be divided into pages and the physical memory will be divided into blocks, fixed size blocks referred to as frames. One thing to note here is that the size of the frame and the size of the page will be the same, and it should be the same. And who is deciding the size of this frame is the underlying hardware. So when a process is to be executed, the pages corresponding to those process should be loaded into the available frame within the physical memory. And since we are loading the process from the hard disk to the main memory, there is a requirement that the hard disk or the backing store should also have the same size as that of the pages or frames. So that is what is illustrated in this slide. Assume that we need to execute a process, namely A, and the size of that process is 4K. So with logical concept, with the concept of paging, we will be dividing our logical memory, namely the process A will be divided into different pages. And assume that the size of the page is 1K. So for a 4K process, there will be 4 pages which is numbered as page 0, page 1, page 2 and page 3. That is what is illustrated on the left hand side of the slide. And in the previous slide, I have told that the physical memory will also be divided into frames. The size of the frame will be the same as that of the page. So here we have assumed that the size of a page is 1K. So here the size of each frame is also 1K. So we are having 7 frames numbered from 0 to 6. and you can see the explanation as physical memory is divided into frames. So that is what is represented in the middle diagram, and one on the right hand side shows the hard disk is also divided into blocks. Here also each block is having the same capacity as 1K. So we know that for a process to be executed, it should be loaded into the main memory. So here the process to be executed is process A, and the process A is having 4 pages numbered 0 to 3. And since paging allows non-contiguous memory allocation, we can see that in this illustration, the page 0 corresponding to process A is loaded into the frame, namely 3. That is, page 0 is loaded into the physical memory in the frame 3. Likewise, page 1 of the process A is loaded into frame 0. That is why in the middle figure corresponding to 0, it is written as page 1, which means that the page 1 of process A is loaded into the frame 0. Likewise, page 2 of the process A is loaded into the frame 5, and page 3 of the process A is loaded into frame 1, assuming that frame 2, frame 4 and frame 6 are already occupied. So that is why we are telling that the logical memory is divided into pages, physical memory is divided into frames. The size of a page and the size of a frame will be equal. Here the size of page or frame is equal to 1K. Now that we have seen the concept of logical memory and physical memory, there is a requirement to convert the logical address to physical address. With segmentation, we have seen that this is achieved using the segment table. In paging, we will be making use of page table to convert the logical address into physical address. So a logical address generated with the concept of paging will be having two tuples. First one specifies the page number and second one specifies the displacement. Here the page number is represented using the small letter P and offset is represented using the letter D. So page number is used to index into the page table. And what is the information that is stored in the page table is the corresponding frame numbers of the pages. That is, in which frame should that page be loaded. And displacement stores define the physical memory address that is sent to the memory unit. So we can see how the logical address is converted into the physical address. So as already told that the CPU will be generating the logical address. So logical address generated by the CPU will be having two parts. First part is the page number and second part is the displacement. So using page number we will be indexing into the page table, from which we will be getting the information regarding the frame. That is, in which frame will that page be stored. And the displacement will be added to that so as to get the corresponding physical address. So this is how a logical address is converted into the physical memory. And we will be seeing problems based on how we will be converting logical address to physical address, or what will be the logical address and physical address for a given question, like that. That time the things will be clear for you. So this is a detailed example. Here we can see that there is a logical memory on the left hand side and you can see the physical memory on the right hand side, and in between you can see the page table. So what is the meaning of this figure is that a process is to be executed and that process is having 4 pages That is what is represented in the logical memory as page 0, page 1, page 2, page 3. So each of the pages of this process has to be loaded into the physical memory. Only then that gets executed. And we have seen that how the logical address is converted into the physical memory is using the concept of the page table. So corresponding to each process there will be a process table. So when a process is to be executed, it has to be loaded into the memory. Say for example, the page 0 is loaded into the frame namely 1. And the page table will be updated like this. That is corresponding to page 0, you will be having the value 1. Because we have seen that it is using the page number we are indexing into the page table. So the page number is 0. In the page table it is written as 1. Meaning is that the page 0 is stored at the frame 1. That is why in the right hand side corresponding to 1 it is written as page 0. Likewise in the page table corresponding to 1 it is written as 4. The meaning is that the logical page 1 is stored onto the frame namely 4. Page 2 is stored on the frame namely 3. Page 3 is loaded into the frame namely 7. So that is what is represented using the grey color on the right hand side. That is the relevance of page table. So from the page table we will be getting the information regarding the frame. That is in which frame that particular page gets stored. And the size of the frame or size of the page is defined by the underlying hardware. And the ideal page sizes is ranging from 8 KB to 4 KB. That is, if the size of the page is too large, there is no advantage of paging. And also if the size of page is too small, there is an overhead of storing and accessing the large page table. And one thing to note is that whenever we are specifying the size of a page or frame, it will be in powers of 2. Why it is in powers of 2 is to make the splitting of logical address into page number and page offset easy, and also to make the translation from logical address to physical easy. So in general we can say that the size of the logical address space is 2 power m and the size of the page is 2 power n, then m minus n bits will be representing the page number and n bits will be representing the page offset. Remember, with paging concept, a logical address generated by the CPU will be having two parts, page number and offset, of which P is used to index into table and D is the displacement within the page. This is already discussed why we are representing page size as always powers of 2. This was asked as an university question. So in order to perform arithmetic on address to calculate the page number and offset easy, we are splitting this. And also that makes the translation from logical address to physical address easy. We can see a detailed example. Consider that the logical address space is 16 bytes and the physical memory size is 32 bytes. So 16 when represented in powers of 2 is 2 power 4 and 32 bytes when represented in powers of 2 is 2 power 6. In this example, we are considering that the size of the page is 4 bytes, which means that in each page I can hold 4 bytes. So just have a look at the left hand side figure where logical memory is represented. always the pages numbers will be starting from 0. So here in this representation of the logical memory, there are 4 pages numbered: page 0, page 1, page 2 and page 3. In page 0, in each of these pages I can store 4 bytes. That is why in the page 0, it is numbered from 0 to 3, corresponding entries as A, B, C, D. Which means that in that page 0 I am having 4 bytes, namely A, B, C, D. Next page is page 1, which is starting from 4 and ending in 7. Again that is 4 bytes in which I have stored E, F, G, H. Next page is page 2, starting from 8 to 11, in which the information stored is I through L. And the last page is starting from 12 and ending in 15. Here also I am having 4 bytes. That is what is meant by the size of the page is 4 bytes. In each page I can store 4 bytes. So total there are 4 pages: page 0, page 1, page 2, page 3, starting from 0 and ending in 15. So depending upon the number of pages, the page table will be having that much entries. So in this example I am having 4 pages. So the page table will be having 4 entries corresponding to each page, namely page 0, page 1, page 2 and page 3. So that is what is represented in the middle figure as page table. The index values are 0, 1, 2 and 3 corresponding to the pages. And what is represented within that table is the frame in which this process, each of these bytes will be stored. Each of these pages will be stored. So using page number, consider the example, we can see where this page 0 will be stored. So we will be indexing into the page table with the value 0. So corresponding to 0, you can see that the value written is 5, which means that this ABCD will be stored in the frame, namely 5. So you start numbering the physical memory from 0. So what is represented as 0 is the frame 0. What is represented as 4 is the frame 1. What is represented as 8 is frame 2, so on like that. So you can see that the frame 5 is one starting with 20 and it is at the location the ABCD is stored. I'll tell one more example. You can see where the page 3 is stored. Here in the logical memory, the page 3 is starting from 12 to 15. So the page number corresponding to that is 3. Indexing into the table, we are getting the frame number as 2. So frame number 2 is start numbering from 0. So you will be getting 0, 1, 2. 2 which is marked as 8. So you can see that correspondingly MNOP is stored there. So always remember that the pages and the frames will be numbered from 0. Explanation is given. The same explanation is given. Now we can do some problems and you can expect these problems for university exam also, and this is very important. So it is given in the question that consider a logical address space of 64 pages of 1024 words each, which is mapped onto a physical memory of 32 frames. I have to identify the number of bits in the logical and physical address. So in order to find the logical and physical address, first we have to represent the information given in the question in powers of 2. So look at the question. It is given as the logical address space is 64 pages. That is, the total number of pages is 64 pages and the capacity of each page is 1024 words, which means that in each page I can store 1024 words. Likewise, I am having 64 pages. So the total capacity will be the number of pages into 1024. So here the number of pages is 64. 64 when represented in powers of 2 is 2 power 6. Likewise 1024 when represented in powers of 2 is 2 power 10. So the total capacity of the logical memory is the number of pages into the size of each page. So 2 power 6 into 2 power 10, which is equal to 2 power 16. So whatever value you are getting as the power value for 2, that is the number of bits in logical address or physical address. So corresponding to logical address, you got the value as 2 power 16. So the number of bits in the logical address is 16 bits. Now the second part is you have to find what is the total number of bits in the physical address. In the question it is given that there are a total of 32 frames. It is not explicitly specified what is the size of each frame. But we have to understand implicitly from that the size of the page and the size of a frame is the same. So in the former part of the question it is given what is the size of a page, that is 1024 words. In a page I can store 1024 words. So that applies to frames also. In a frame I can store 1024 words. That is why it is only given the number of frames. So 32 when represented in powers of 2 is 2 power 5. And each frame is having a capacity of 1024. 1024 is equal to 2 power 10. So the total capacity of physical memory is equal to number of frames into size of each frame. That is equal to 2 raised to 5 into 2 raised to 10, which is equal to 2 raised to 15. So here got the power value as 15. So the number of bits in the physical address is 15 bits. We can see a second question. Again in this question it is given what is the total number of pages in the logical address and what is the size of each page. And also given what is the total number of frames. Do the same calculation as in the previous question. In order to find the capacity, you need to multiply the number of pages into size of each page. Here the number of pages is given as 256. 256 when represented in powers of 2 is 2 power 8. 4 kb, 1 kb is equal to 2 power 10. So 4 kb is equal to 2 power 2 into 2 power 10. So total capacity equal to 2 power 8 into 2 power 2 into 2 power 10, which is equal to 2 power 20. So the number of bits in the logical address is 20. Likewise, we have to implicitly understand that the size of each frame is also 4 kb. So 64 when represented in powers of 2 is 2 power 6. 2 power 6 into 2 power 12 equal to 2 power 18. So the number of bits in the physical address is 18 bits. Next question. In this question, you are directly given what is the total number of bits in the logical address and physical memory. You need to identify what is the total number of entries in the page table and frame table. So I have told that depending upon the number of pages, we will be having that much entries in the page table. So how we find the number of entries in the page table is that you have to divide the total logical address is divided by the size of each page. So here it is given that the logical address space is 32 bit. So 32 bit means that the total addressing capacity is 2 power 32. The size of a page is given as 4 kb, which is equal to 2 power 2 into 2 power 10, which is equal to 2 power 12. So the number of pages is equal to the total total size of the logical memory divided by the size of each page. That is equal to 2 raised to 32 divided by 2 raised to 12, which is equal to 2 raised to 20. 2 raised to 20 means that is equal to 1 MB. So page table will be having that much number of entries because we will be having that much number of pages. Likewise, the frame table will be storing the total number of frames. So again, in order to get the information regarding the number of entries in the frame table, you need to make use of the capacity of physical memory. Physical memory here it is given as 512 MB. So 1 MB is equal to 2 power 20. So 512 MB is equal to 2 power 9 into 2 power 20. So number of frames is equal to 2 raised to 29 divided by 2 raised to 12, which is equal to 2 raised to 17, which means that there will be 128K entries. So in the first two questions you are asked to calculate the logical address, and in this third question you need to identify what is the number of entries in the page table and frame table. Number of entries is equal to the number of pages. Now we can see whether paging suffers from external fragmentation and internal fragmentation. So you can see that with paging there is no external fragmentation. But paging suffers from internal fragments. That is, we assume that the size of a page is 1K. So consider a process that is having the size as 5K. Okay, that is having the size as 5K, and the size of each page is 2K. So what happens is that when we are dividing this process into a size of 2K, we will be having 2K and then 1K. So when this 1K page is loaded into the frame which is having the size as 2K, the 1K space is wasted within that frame. That is why we are telling that paging suffers from internal fragments. That is, it is not mandatory that always the size of the process should be equal to that of the summation of size of the pages. There can be some space, there can be some gap that is occurring because of the fact that the size is not exactly the same. So a typical example is given here also. May refer that. So with paging, when a process arrives in the system to be executed, its size, which is expressed in pages, is examined, and each page needs a single frame. So if there are n pages, then there should be at least n frames in the memory. And if that frames are available, the process will be allocated the frames. That is, the first page will be loaded into one of the allocated frames, and the corresponding frame number will be put in the page table for this process. Likewise, the next page is loaded into another frame and its frame number is put into the page table, and so on. Consider that a new process is to be executed, and that process is having 4 pages, namely page 0, page 1, page 2 and page 3. And currently the free frames that are available are numbered as 14, 13, 18, 20 and 15. So when we refer to the left hand side of this slide, before allocation you can see that the spaces that are vacant are marked as grey, that is 13, 14, 15, 18 and 20. This much frames are free in the memory. So for this new process to be executed, it requires 4 frames. Currently we are having a total of 5 frames that are free. So it means that that process can be executed because that much number of frames is available. Now what is represented on the right hand side is that after the frame has been allocated to the new process, only the frame that is remaining is 15, and you can see that correspondingly the page table is also updated. That is, page 0 is loaded into frame 14, page 1 is loaded into frame 13, page 2 is loaded into frame 18, page 3 is loaded into frame 20, frame number 20. So operating system will be keeping track of the number of frames that are available in the frame table. Because it is this operating system that is managing the physical memory, it should get an idea regarding how much memory is allocated and how much memory space is remaining. That information will be there in the frame table. That is the relevance of frame table. And frame table will be having one entry for each physical page frame, indicating whether it is allocated or not. Next is the details regarding the hardware implementation of the page table. And depending upon the operating system, it has its own methods for storing the page table. And the hardware implementation of the page table can be done in several ways. And the simplest way to implement the hardware page table is using a registers. Registers should be built with very high speed logic to make the paging address translation efficient. But we can use registers for page table implementation only if the size of the page table is small. Say for example, if the page table is having only 256 entries. But in contemporary computers, the size of the page table is very large. Say for example, it might be having 1 million entries. So it is not possible to use registers to implement page table in this case. So instead of that, the page table is kept in the main memory and a page table base register points to the page table. Changing page table requires changing only this one register, which can reduce the context switch time. But the problem with this approach is the time required to access a memory location. For example, if we want to access location I, we must first index into the page table using the value in page table base register offset by the page number for I, which requires a memory access. It then provides us with the frame number, which is combined with page offset to produce the actual address. Then only we can access the desired place in the memory. So we can see that with this implementation, 2 memory access are needed to access a byte. So memory access will be slowed down by a factor of 2, which is intolerable. So in order to avoid this, we can use a special lookup hardware cache, which is referred to as associative memory or translation look-aside buffers, in short TLBs. Associative memory, it is a concept that is used to increase the speed of searching. That is, it is implementing parallel search. So with this concept, we'll be having 2 entries, page number and frame number. So corresponding to each page, you will be getting the information regarding in which frame that page will be stored. So we can see the paging hardware with associative memory or translation look-aside buffer. The translation leukocyte buffer is an associative high-speed memory and it consists of two parts, a key, otherwise it is also termed as tag, and a value. So when associative memory is presented with an item, it is compared with all key values simultaneously. If the item is found, the corresponding value field is returned. So we can see what is the meaning of this figure. That is, we have modified the paging hardware by incorporating the translation leukocyte buffer. So when a logical address is generated by the CPU, the page number is presented to the translation leukocyte buffer. If the page number is found, its frame number is immediately available and is used to access the memory. In such a case, we can tell that a translation bit hit has occurred. That is, if the requested page is there in the translation leukocyte buffer, we immediately get the corresponding frame number, and so the physical address can be calculated easily. So that is what is referred to as TLB hit. Now when CPU requests a page and using the page number, we are referring into the translation leukocyte buffer, and if the frame number corresponding to that particular page is not there in the translation leukocyte buffer, then only we need to refer to the page table so as to get the frame number. So what happens is that with the concept of TLB, the speed of accessing the memory can be increased. That is, it is like that of a cache memory. And periodically this translation leukocyte buffer will be updated. So if the entry is there in the TLB, it is referred to as TLB hit. The entry is not there in the TLB, it is referred to as TLB miss. Now we can see how memory protection is ensured with the concept of paging. For this, we introduce a bit, namely valid and invalid bit associated with each entry in the page table. Valid indicates that the associate page is in the process logical address space and is thus a legal page. Invalid indicates that the page is not in process logical address space. For example, refer here. Here on the left hand side, what is represented is the logical memory. On the right hand side, what is represented is the physical memory. Between you can see the page table. Previously, the page table was containing has only one entry regarding the frame number in which that particular page is stored. So in order to implement protection, the page table has been modified so that it is having two entries, that is V and I, which means that whether it is a valid or an invalid one. That is, if this bit is set to valid, the meaning is that the associate page is in the process logical address space and is a legal one. If it is set to invalid, the page is not in process logical address space. So that results in an error. And the operating system disallows the access to the page. So in this example, the logical memory is having 6 pages, page 0 through page 5. Now, if this process is trying to access a page, namely 6, you can see that corresponding to page 6, it is represented as 0I, which means that I means that it is invalid for that particular process. Corresponding to 7 also, it is represented as I, which means that that particular process is not having a page, namely 6 or 7. So only pages it is having is 0 to 5. So you can see that corresponding to 0 to 5, all the entries it is marked as V, which means that it is a valid page for that particular process. Rest is the same. That is, page 0 is loaded into frame 2. Page 1 is loaded into frame 3. It is a valid page. Likewise. Now if you are comparing paging and segmentation, segmentation can be applied when we are dividing a program into chunks of different sizes. But paging requires that the chunks should be of the same size. Segmentation is done by the programmer, whereas paging is done by the compiler or MMU. And segmentation suffers from external fragmentation, but paging suffers from internal fragmentation. And this is a table that shows the difference between paging and segmentation with reference to factors length, address space, dynamic address translation, protection, sharing, fragmentation, linking and loading. And please make use of this table for exam, because you can expect a question between the difference between paging and segmentation. Thank you.